Okay, so let's go. Circle motion.
Began according to plan as they leapt off the bridge while tethered to the cable.
Stand up. On three, go. On three, number. One, two, three, go.
But as the team was about to reach the end of their first arc, the cable snapped, and 4 men and 1 woman plummeted 70 feet at 80 miles per hour, slamming into the water with terrifying force.
Okay, I'm on the outside helmet cam. Kenny, myself, boy, Sarge. She does the front flip. Here we come, going into full velocity right here. Probably reached about 78 miles an hour, right about here, 78 miles an hour. You'll see the harness disconnect from the cable right there. Didn't see, just disconnect. My arm goes out, and here we come to the water. Pow! Oh, with a ton of bricks. So look at the splash, like 40 feet. Wicked action, though.
Again, according to
outside helmet cam. Here we come, going into full velocity right here. Probably reached about 78 miles an hour, right about here, 78 miles an hour.
All right, so the cable is going to snap.
You'll see the harness disconnect from the cable right there.
The question is, did they get the wrong cable? Did they pick a cable with the wrong tolerance? So what do you have? You got like 5 people, approximate weight. I'm going to say about 900 to 1,000 pounds. They end up picking a cable that has a tolerance which is about 1,000 pounds. Is that the reason why they snap? You got five daredevils, and you know they're going to do something stupid. And I thought that's exactly what happened. I thought they end up picking a cable with the wrong tolerance.
My arm goes out, and here we come to the water. Pow!
So
it looks like Spicoli.
Yeah. So as I was running the numbers, I noticed something. I noticed was this guy said.
Okay, I'm on the outside helmet cam. Kenny, myself, boy, Sarge. She does the front flip. Here we come, going into full velocity right here. Probably reached about 78 miles.
He said 78 miles.
No, right about here, 78 miles an hour.
78 miles per hour.
You'll see the.
He said 78 miles per hour, and then that's exactly what you should get if this cable is 200 feet. It is. So which means that somebody had done the calculations for him. They knew that we're going to be going at 78 miles per hour. So which means that they must have figured out the amount of tension that we're going to induce on the cable, maximum amount of tension at that speed, and which means that must have a cable that was going to be able to tolerate more than that tension. So which means that must have bought the right cable. So the question is, what went wrong? There's a lot of physics in that.
The speed is critical. I need to make sure that I hit the magic number to drive through the loop. Otherwise, it's not going to be possible. So I have to concentrate on that and just concentrate.
All right. So the magic number to complete the loop.
Just calm.
This is Jaguar. 80th year anniversary of Jaguar.
Myself down.
It's very impressive.
I was probably the most calmest that I've been all day when I was in there and I was driving down and approaching the loop.
I mean, being able to loop the loop is impressive, but you need to know what the magic number is. Be able to exceed it, right? If you don't reach the magic number, you're not going to be able to loop the loop. And Jaguar was able to do that on its 80th year anniversary. Versus a Ford Tempo.
You're looking at style and technology in total harmony. It's the new 84 Ford.
Wow, so Ford Tempo was able to do that in 1980s.
Ford Tempo. Tempo's unique aerodynamic design contributes to mileage this high. There's technology like 4-wheel independent suspension to absorb impact. A new high-swirl combustion engine.
One of the cheapest, the most economical and destroyers cars that you could ever buy.
With power.
I bought it when I was in grad school.
And Tempo's front-wheel drive delivers responsive handling and good traction.
So, for you to be able to loop, how do you know what the magic number is?
Tempo. Have you driven the best-built American cars? Have you driven a Ford lately?
All right, your first ride is going to be that gradual onset ride to a maximum of 7 Gs. Are you ready?
Remember we were talking about male versus female? G-load tolerance.
Yeah, right.
And we talked about the body shapes, distribution of fat.
Are you ready?
Yes, sir. I'm ready.
Ready. 3, 2, 1, engage. How you doing?
All right, so G-load is right here.
lose all the green. Tell me now and start that lower body strain, okay?
Okay.
Squeeze those legs nice and tight. 1, 2, 3. You're looking real good. Squeeze everything nice and tight.
I'm losing it.
Not yet. It's only 2 Gs.
Okay.
It's only 2 Gs.
You should feel like you're going straight up in the air at this point.
This is awesome.
The 4G right there, you're doing good.
3, 2, 1, engage. Back on the stick. On top. On top, breathe. You're on top, breathe. You're on top, breathe.
I'm losing it.
Okay, big breath, walk off and hold it.
You're on top, breathe.
Hold.
On top, breathe. 1, 2, 3.
1, 2, 3. No cheater breath.
1, 2, 3. 1, 2, 3. 1, 2, 3.
All right.
Go.
Legs tight. Foot tight. Breathe.
1, 2, 3.
1, 2. Hold. Okay. Stay tight, stay tight, stay tight, stay tight. Hello? Are you with me? You coming back around? Hello? How you doing?
What?
Hello, Will?
Hello.
Will, sit up.
I'm up.
Sit up.
What?
You're up? Put your head up.
It is up.
Put your head up.
Oh.
Do you know what happened?
Yeah.
You ate lost.
Yeah.
What happened?
I'm taking out you are.
All right.
I've seen the same behaviors in bar crawls.
What?
Bar crawls.
You going nauseated? Yeah, a little bit. I'm gonna vomit. Okay, get the bag. Get the bag. You want that beef?
Yes, you did really well.
It's okay.
I actually
This girl,
have no comments for you.
she's skinny as hell.
Everything looks real good.
She don't lose it.
How you feel?
She was fine.
Good job.
I think that guy also did well. It's the body type. Women tend to do better in general. Basic weapons.
Holy smokes! Okay, all right, okay. Yeah. Okay, I want to sit back.
He's out.
I think I blanked out. Okay, oh my god, upside down! You said it didn't go upside down! You said it didn't go upside down! Oh, I get it down! Okay, sorry, so that wasn't so bad, was it? Oh my god, right this, oh Lord, I get it! Oh, okay, he's doing this on purpose. Okay, my legs, I lost feeling in them, okay? It's okay.
Sorry.
I'm still laughing. Oh my god.
Well, okay, okay, my legs don't work anymore. I think I left my lung up there.
What did you do? Where are you yelling?
This guy's still out.
How was that? Is that pretty cool? Josh, you still with us? You know, it's just a question while you're strapped in. If you'd like to do one more time, stand backstage. Let's do it again. Let's do it again. Let's do it again. Let's do it again.
That guy had a G-lock a couple of times.
Sergeant on the call, fighter.
That guy's got very good certification, obviously. All right, guys. So we talked about centripetal acceleration. So this is your acceleration term. So mass times acceleration is going to give you the force, right? So that's known as the centripetal force. So speaking of the
The
centripetal
center
force,
post, the cameraman films dizzy doings as the more daring of the rotor riders defy centrifugal force, or try. The rotor ride is a snap, unless you're the squeamish sort.
On a centrifuge, positive G's pin you to the seat of your pants.
so this is centrifugal. It's known as a rotor.
All extreme rides are designed to subject us to as much positive G as possible, because the body is much better at coping with them.
So here's a question for you. What is the centripetal force in a rotor? All right, so those of you guys ever been in a rotor, give yourselves 5 points. It's kind of a neat little thing. So you spin it so hard that you become suspended on a wall, and then they lower the ground floor, and you remain suspended there. All right, and it feels like you're lying on top of your bed if you close your eyes. It's a neat little feeling. All right, so if that's the case, you're inside a rotor. What's the centripetal force acting on? All right, so this is a new topic. Topic is the centripetal force. All right, so it's the same as this circular motion. All right, so you got this object moving in a circle. It doesn't need to be moving at a constant speed, as long as it's moving in a circle. So let's just, for now, let's assume constant speed. It's not a big deal. All right, so this circle is going to have a radius. R is the radius. And obviously, it's going to be accelerating in this direction. So that's the centripetal acceleration. And we have an expression for the centripetal acceleration, which is going to be v squared divided by r. And what's causing the acceleration is the force acting on it in this direction. Here's the force, and the force is going to be acting on this mass. All right, so by definition, the force is what causes acceleration? Acting on this mass. So notice that this is a centripetal force. Okay, I messed it up. All right, so this is the force directed towards the center, causing an acceleration which is directed towards the center of a circle. All right, so this is known as the centripetal force equation. All right, so if you're thinking about it, what happens is this acceleration is the same as that acceleration. As a result, the centripetal force formula looks like this. All right, so this is the way it is done in physics book. Except what does it mean? What's the meaning of the centripetal force? What is the centripetal force if you're inside a rotor suspended on a wall? All right, so here's your rotor. and they're going to be spinning this thing so fast. So they're going to be spinning it in this direction. So you will have the sort of speed in that direction. And then the mass is going to become suspended on the wall. So the question is, what is the force directed towards the center, if that's the case? Centripetal force is a force directed towards the center. So the question is, what is the nature of this force? All right, centripetal force simply means any force directed towards the center of a circle. Any force, radial forces are known as centripetal forces in circular motion. So what is the force directed towards the center in circular motion? What I'm asking is, what prevents you from going in a straight line at constant speed when this thing is spinning? Right? Your body wants to go in a straight line at constant speed, and something prevents it. What prevents you from going in a straight line at constant speed? It's the wall, right? I mean, if it weren't for the wall, you would have been going in a straight line at constant speed. Because of the wall, you're not able to do that. So you're pressed up against the wall because of your inertia. Your body wants to go in a straight line at constant speed, and the wall prevents it from happening. So what kind of force do you experience from the wall? The normal force, the surface force. So the force which is directed towards the center is the reaction force from the wall. So that happens to be the normal force. So the centripetal force happens to be the normal force. That's what it is. So when somebody says what's the centripetal force, what they mean is what's the force which is directed towards the center. In this case, the force directed towards the center is the normal force. But when a satellite orbiting the Earth, what's the centripetal force? So what is the force which is directed towards the center? What is the center seeking force in this case? Well, in that case, the force which is directed towards the center is going to be the gravitational force. So satellite orbiting the Earth, so this time the force which is directed towards the center is going to be the centripetal force. Speaking of the satellite, it could be the moon orbiting the Earth. All right, so what is the force which is directed towards the center? It's going to be, so what is the centripetal force in this case? It's gravitational force. Capital G, the big mass, which happens to be this, times the small mass, which is the mass of the moon, divided by the square of the distance, all the way out there. So in this case, the centripetal force is the gravitational force. Well, when a car is negotiating a curve, what is the centripetal force? Right, so notice that is the centripetal force. It's just negotiating a curve right there. What keeps the car on the road? What prevents the car in a straight line constant? So going back to the same question. What is the force that keeps the car on the road? Prevents it from going in a straight line at constant speed? It's the frictional force, right? So what kind of friction? Static friction or kinetic friction? This one is sliding friction, so you don't want that. This car is not sliding, so it's got to be experiencing static friction. So what keeps you on the road? What keeps you on the road is the static frictional force on a curve. All right, so this is circular motion. This section is circular motion. So whenever you're negotiating a curve like that, force which is directed towards the center is going to be static frictional force. So that's your static frictional force. So whenever you're inside the rotor, it's going to be the normal force. Whenever you're negotiating a curve, just like that, let's just do a curve. All right, we managed to do a curve right there. All right, if this is a car moving at the speed, all right, so the force which is going to be directed towards the center, the centripetal force is going to be the static frictional force. In this case, the force is going to be static frictional force. All right, let's have a quick little discussion on this. Okay, looking in this situation. A couple of things. There's a lot of physics here that we need to focus on. You know, there's a speed limit on the side of the road, right? My guess is the speed limit is probably about 35 miles per hour. Right, so whenever these people come up with these speed limits, speed at which you can negotiate a curve, does that change from vehicle to vehicle? All right, so the maximum speed at which the vehicle is going to go into a skid for slide, will it change from vehicle to vehicle? Does it depend on the mass of the vehicle? Does it depend on the weight of the vehicle? What do you guys think?